This video has been developed to help people understand the water quality effectiveness evaluation. We will be looking at roads and streams and how streams are impacted by sediment delivery.
Welcome. Today, we will be looking at the evaluation of fine sediment generation and site management for industrial roads in BC and the Water Quality Effectiveness Evaluation, or WQEE app. This tutorial is split into two parts. In this first video, we will look at some background, and in the second video, we will go through a sample site and how you will use the WQEE app to complete the evaluation. How do you look at sediment and erosion, and how do you decide what is important and what isn't important? We will look at many examples of sediment sources and how you can make a quick assessment on if this issue is something that should be dealt with now, and if so, what can be done about it. It is important to know what is causing water degradation and what isn't. What we will look at today will be how we estimate and prioritize fine sediment delivery from disturbed industrial sites to streams. When we talk about fine sediment, we are actually including a lot of other things that are transported along with fine sediment, sometimes organic material, fecal coliform, pesticides, herbicides, and or even things like hydraulic waste oil, because the same sites where we are doing our assessments determining fine sediment generation should be the primary focus for a wide range of other water quality contaminants. In other words, if you are going to do a spraying program of herbicides in an area that isn't subject to surface erosion and without the ability to be connected to the stream, then it is impossible for that material to get into the stream. So there is a difference between mere proximity to a stream and actual location of disturbed mini catchments with direct surface connection to a stream. The important thing would be to avoid spraying within designated mini catchments in order to avoid that material reaching the stream. When we do these assessments, we are looking for any place where the increased surface flow from that road or cut block, or even a landslide surface that allows the surface water to reach the natural stream that would otherwise be impossible. So in this example, we look for wherever the road crosses a stream, there is an opportunity for sediment from that road to reach the stream. If a road parallels closely to a stream, a relief culvert can carry sediment from the road, run over land, and deliver it to the stream. Also, places where there could be a landslide or a switchback somewhere up the road, which could concentrate enough flow, which could cause formerly subsurface flow to come to the surface and be able to flow to the stream and carry sediment with it. When you are building a road and you open up bare soil, you are leaving the ground open to erosion. This is most apparent when you are under the construction phase, or in this case, when someone is cleaning a ditch line. It takes some time for the disturbed ground to re-armor and revegetate, and during that period, it's going to erode. Whether that erosion product reaches a creek and becomes sediment or not is a key part of the evaluation. On the other hand, there are other types of mass failures where you have a lot of material moving en masse. The site slope can liquefy, or there can be many different processes by which a large chunk of parent material can run off a road or landscape right into a creek. Soils laid bare by landslides or gullying may then undergo a cycle of further surface drainage incision, supplying chronic sediment loads to a creek. The first question when you look at a site should be, is this site eroding? To start off, it is important to understand that every gravel road surface will erode, but not every site will generate sediment. The wetter a road is, the more traffic that is on a road, the more fine unconsolidated material it will generate. You need to have fine sediment in the road surfacing material to bind the materials together. But when there is heavy traffic on it, for example, logging trucks or other heavy equipment, they pump sediment up through to the surface, and then the rainfall carries that unconsolidated material off the road. A measure of the actual erosion being generated from identified mini catchment components is the first consideration. Once you create unconsolidated fine particulate matter, is it being transported away from the site, or is it staying put? Is it running down a ditch line and into a culvert? Might that culvert outlet be connected to a stream? If so, then it is something of interest to our analysis. Next, we look at if that sediment actually reaches a creek. You will find that lots of erosion products generated by roads will not reach a stream. Although losing fines may be damaging to the road surface itself and be of great importance for road trafficability, it really doesn't affect water quality. Fines generated by surface erosion but not able to be carried to a natural surface drainage does not contribute to water quality degradation. Traditional GIS-based watershed management procedures, total area harvested, ECAs, the length of road, or the number of bridges have been used as indicators when evaluating hydrological impacts of human disturbance on a watershed. Unfortunately, if the level of management is not integrated into the analysis, the evaluation is useless for determining how to manage the watershed better. It merely flags the fact that a watershed has undergone human disturbances. What is important, however, is how the roads have been constructed and managed. If you have done a good job with road design, location, construction, and management, your equivalent clear-cut areas, or ECAs, and other indicators become largely irrelevant. 20 well-designed and managed stream crossings may have much less impact on a watershed than one badly designed and managed stream crossing. Unfortunately, ECAs are still commonly used in many or most of BC's watershed evaluations because they do not require expensive field assessments and academically at least seem reasonable. However, good road builders and watershed managers are penalized if quantity road infrastructure and not quality of management is the basis for evaluation. Finally, once you have done an assessment of several sites within a landscape, from those assessments on the sites, you can ask yourself, where can we make a difference? Where can we make an improvement to the water quality of a site with a high level of fine sediment generation? There may be issues associated with greater berms. There may be issues with a misplaced culvert or a bridge deck, or a bridge built with a deck below grade so that water runs onto the bridge rather than away from it. There can be many different types of problems. Some will be easy and inexpensive to overcome, and others will be very expensive or even not possible to change. Therefore, when prioritizing sediment impacts, you must tie it to the cost of improving that site with the potential benefits accrued from addressing those impacts. If the only thing you can think of to do is changing the location of the road to reduce sedimentation, then this may not be feasible. However, it could just take a training course for grader operators to teach them not to leave berms open over streams. Simple, inexpensive fixes may be possible. Identifying natural drainages in the field at first may seem like a simple thing to do, but in the dry season, there are lots of landscapes where you don't know where surface or subsurface water will be flowing. Although we have trim maps that locate the majority of streams, when you get it into the field, you will find streams that pop up where you didn't expect them. And in some locations, especially in the interior, where trim seems to think there are streams, but in fact, no streams exist. There are many sites where water is running through the ground, but it's not captured by any surface feature whatsoever. You have to wait until you build the road, and when there is rainfall, you will see water coming out of the side slope. It may be gushing out from one spot, like this photo, or it may be along a whole slope length. But the ditch then will be carrying a lot of water, and that water may be carried down to the stream and potentially carry a lot more sediment than if that water had remained on its original natural drainage way. This is sometimes what you see when you drive down many roads, both in the interior and on the coast after spring melt. You've got unexpectedly heavy discharge in ditches that generally shouldn't have had that much water in them a few days after the rainfall has ended. The most common explanation to the public is that it is caused by the ECA's upslope being too high, thus causing these negative hydrological impacts. In the WQEE developers' experience in hydrological degradation, the vast majority of issues associated with increased stream flow reflect the way the road's drainage network has been managed, not the amount of harvesting. If you have a lot of small drainages that are directed away from their natural course, and you have ditch lines that intercept and redirect surface and subsurface flow, these issues, not ECA per se, have caused the negative hydrological impact. So when you think about ECAs, you really shouldn't be thinking about the area that is harvested. You should be thinking about what kind of job you did on your road systems. That is the most important thing when we are thinking about impacting water quality and change to timing of flow in a given area. Now we will move on to doing an example assessment using this water quality effectiveness evaluation FREP program. Once you've selected your site, we'll use this bridge crossing example. You need to define the mini catchment that sends water toward the bridge and the stream. Now, use your imagination and pour buckets of water all over the place. You want to imagine where this water is going. So have a look at those blue arrows, and that's where you'd imagine the water would be flowing. All the water that is flowing to the bridge will be grouped together, and the water that is flowing away from the bridge and stream is not part of the unit. We are only concerned with the potential erosion components that are draining into the stream. Notice there is heavily disturbed ground with high sediment generating potential there on the right of the slide. From the water quality assessment point of view, it isn't tallied because that sediment will drain off to the right into the forest and be filtered away, so it won't reach the stream. Whereas the water that is running within the mini catchment highlighted in red is going to run down to the bridge and will eventually reach the creek. When we do our assessment, we are only concerned with those areas that drain into the stream. In some cases, you look at a road surface and think, oh, that road looks okay. This is the Dakota Creek Road, and it has 300 meters of road without a culvert. Sometimes you can get away with that and not have an effect on water quality, but in this particular case, there's quite a bit of water generated on the up road side, the left side of the road. This runs down in the inside road ditch, crosses the Dakota main line, and runs for 200 meters across a very flat glacial fluvial terrace, and then abruptly flows over the 20-meter escarpment and creates this huge gully. So this particular road segment looks innocuous and benign. However, the way the water is generating and where it is being sent is creating a huge gully feature that is producing in the order of between 500 and 1,000 cubic meters of sediment each year. This is going directly into salmon-bearing portions of Dakota Creek as well. So this, by about tenfold, is more important than anything else that is happening in this watershed at this time. However, it might not be recognized if you just drove along the road without considering how much water is flowing in the ditch lines and where that discharge might be going. Now, to give you a size of this gully, the rock on the right is approximately half the size of a pickup truck. It's a very large gully. If you ever see a lot of captured road water sent towards an escarpment or a terrain class 4 or 5, you have to anticipate something like this might happen. When looking at this bend in a stream, as shown in this slide, you may think that, of course, there's undercutting from this stream, and that this slumping into the stream is a result of natural processes. The way a geoscientist looks at that is, yes, there will indeed be some mass erosion, but if there is some artificial road water being generated upslope that is running over the head wall of that bank and causing it to fail, then we will have to say it was being accelerated by human disturbance. In this case, there is indeed a large amount of water being dumped by the road just above this head wall, and therefore If you have been responsible for the construction of this road, then you are also at least partially responsible for accelerated sediment input into this stream system. So now you've collected the sediment and you're moving it, channeling it downslope. Then you have to say, well, what are the options to deal with that discharged water? I could send that water onto a big open slash. And if there's 200 meters between the outflow of the stream, you can see the sediment will not reach the creek. The coarser material will drop out of the water in the first 5 or 10 meters in the slash, and the finer material, if it is hummocky ground, will drop out again with a further 15, 20, 30 meters. There is no change to the hydrology of the site, nor change to the water quality, because the sediment and water is being reabsorbed into the soil. Another option would be you have a ditch line that runs directly into a creek. In other words, everything upslope of that ditch line is now part of the problem. And everything that you calculate coming off that cut bank road, any skid roads, anything flowing into that ditch line upslope is tallied when you're estimating the amount of fines that are delivered to the creek. There are also examples in between the two discussed, which we won't get into, but just so you know, given the surface area of the component will determine how much surface water can be collected during precipitation events. You must also consider how far over a forest surface this accelerated surface drainage can flow and still bring sediment into the stream. In other words, if the water is being generated in a small area of about 10 square meters, it will only take a couple of meters of filtration over forest floor before it's going to be completely absorbed. On the other hand, if there is 300 or 400 meters of road 6 meters wide, the amount of surface flow will be very high. It might take 100 to 150 meters of flow over forest floor before it's going to be reabsorbed. For this reason, the relief culverts of many roads located parallel to nearby streams are at least partially connected to the stream. So as part of the app, we have tables to show us the portions of sediment we might expect. The estimates are indeed crude, but at the same time relevant to the order of magnitude estimate we wish to make to help direct better management. If we want to use this table, let's look at an area of about 300 square meters of disturbed land. That is 15 meters over forest floor away from the stream. And then, so we would say that has a connectivity of 0.5. It is really important what kind of terrain you are on when considering sediment generating potential. In this case, we are looking at a very fine textured material in the Peace River area. Some of the fine materials in the Powell River area are covered in a coarse sediment, and then underneath this coarse sediment, there are highly erosive lacustrines. Along this creek, there is a large deposit of lacustrines buried under a layer of coarse sediment. If you expose these fines under the coarse sediment, you are open to very serious water quality problems. In every watershed in BC, we look for deposits of gravel for our road bases. They have very few fines in them, and they are used for lots of road capping material. Roads built on such landscapes are generally very forgiving. There's not a lot of sediment to generate, and any water generated is quickly infiltrated back into the soil. A road contractor used to building road on these coarser sediments can come into serious disadvantage when dealing with less forgiving landscapes. The most common road surface soil material in BC is this glacial till. Virtually all of BC was once covered with glacial till, although subsequent glacial retreat has modified the terrain considerably. There is a basal till underneath. It's a highly compacted material. And on the surface, the reddish material is an ablation till, which is virtually non-compacted. It has fallen out during melting of ablating glacial ice. All the root activity, the biology of the forest floor occurs in the surface of uncompacted material. The interface between ablation and basal till is often the sliding surface of major slope failures. In terms of surface erosion, some basal tills are so cemented that if you take a backhoe and dig into them, they actually spark. They don't erode easily. You can almost keep a vertical wall as a cut bank and it won't generate much sediment. The unconsolidated materials are a different story. The ocean level was at about 140 to about 250 meters above its present level at the peak of the last glacial epoch. Around the whole of the Georgia Strait, there are old deltas, lacustrines, and marine materials everywhere at higher elevations than you might otherwise expect. You can get some pretty unpleasant surprises where you run into marine blue clay because these materials behave badly when they get wet. Gravel road surfaces always create sediment. This is something we have to recognize. Sometimes it is obvious in a case like this, but in many cases when you visit the site, especially when dry, it won't be really obvious that it is capable of generating sediment. If you are actively logging a site, you will have no doubt experienced traveling behind a logging truck on a wet day that is spewing up large amount of mud from the road. And meanwhile, lots of pickup trucks have gone by and you haven't seen the mud, but you are seeing it now with a logging truck. The heavy loads result in extreme forces on the roadbed, and hydraulic pumping results that brings fines to the surface, and then those fines will be open to erosion. The more activity there is on a road, the more fine sediment will be generated. The amount of heavy traffic is an important criteria for determining how much sediment will be generated on a given road. Based on all available literature dealing with gravel roads, we have come up with some simple tables that consider road surface sediment generating potential, road slope, and amount of traffic to estimate the amount of surface erosion one might expect from any road over the course of a year. These tables are incorporated into the calculations that estimate road surface contributions to fine sediment generation. We get you to enter the road slope, road surfacing quality, and amount of traffic the road experiences. This generates an estimate of depth of fine sediment generated over the coming year. The depths of erosion range from 0.2 millimeters to 1 centimeter. We are talking about more than an order of magnitude of difference in erosion between little used roads and heavily used roads. These depths of erosion were based on measurements taken both on the coast and in the interior, and obviously heavily used roads generate much more sediment than roads experiencing only light traffic. It is important to determine what type of road you are on to determine the amount of sediment you expect it will generate. Remember, we are not yet discussing what sediment is getting into the stream, just what the road itself is generating. A road could be generating a lot of fine particles, but that sediment may not be connected to a stream and therefore will not play a part in its water quality degradation. This is an example of the Dakota FSR, a 4x4 road, not presently being used by logging trucks, but occasionally by recreational users. It would generate about 1 millimeter of erosion of sediment over 1 year. It has a 3% slope. This is up in Theodosia, Maine, and being heavily used by logging trucks. It would generate 5 millimeters of sediment over a 1 year period. It has a 4% slope. Besides from road surfaces, any other surface from which you remove vegetation and leave bare soil, we come up with a figure that the bare soil will generate 1 centimeter of sediment per year. As soon as the surface starts eroding, it begins the process of hardening up. Basically, this means leaving the soils open to erosion and allowing the fines to be eroded away, leaving behind coarser materials less prone to creating mud. Over 1 or more growing seasons, vegetation will also become established on most disturbed sites. Historically, workers used to leave the surface to harden up on its own, but now we know this isn't a good idea, as hardening up processes generates fines that get into our water systems and clog up spawning beds. When you look at rainfall erosion, wherever there is any surface material, a rock, a bit of moss, a twig, that is enough to protect the surface from rainfall erosion, surface erosion is halted. When the surface is opened up, if there are particles of rock or organic materials, As they come to the surface, as the fines go away, then the rate of erosion will decrease dramatically as the surface hardens. In the first season, you will get a lot of erosion from a cut bank. The second season, substantially less. And by the third or fourth season, between revegetation and the self-armoring from rock and material, the sediment erosion becomes negligible. This is why, in the first year of road construction, what happens to ditch water capturing cut bank material is very important. When we look at this site example, we can divide the site into components. We have cut banks, road surfaces, ditch lines, more road surfaces. And each of these components has a predetermined rate of erosion, and each has an estimated surface area. By multiplying these two together, we can calculate the volume of sediment that will be generated at this site by those components. If all the calculated volume runs directly into the stream, we say that it is all connected 100%. The volume of erosion multiplied by the connectivity provides a measure of sediment actually reaching the stream and thus impacting water quality. We can say that this much sediment is being generated by that road system. In this case, it produces half a cubic meter of fines, and half a cubic meter of fines falls into the low level of sediment generation, which is what you'd expect just by looking at this site. It doesn't look like a problem area. Now we have use of this app to enter all the data into. We will do a quick example of that in the app in the next part of this tutorial, so you can see how we come up with the numbers that we do. If we conduct an assessment using a site like this, we will first ask where the water is going to run. In this case, it will run down these road ruts. Let me just show you. You'd see it would run down these ruts here, onto the bridge and then into the stream, and then maybe down these cut banks here, and down this. You can see all the rutting on this other road surface on the other side. The inherent soil materials are of poor quality and were used in the road surfacing. These materials are easily entrained by flowing water. The multiple rutting of this road is readily apparent. The components we have at this site are 2 road surfaces and a cut bank on either side. So here we have this road surface. And this one. This side. And then you can see we've got this cut bank over here as well. And one on this side. You can see this ditch as well. Won't use that. For all the components in our site, the road surface and the cut banks, we need to make an assessment to determine how much sediment is coming off each of these areas and how connected they are to the stream. In this case, they are all directly connected to the stream. They have a connectivity of 1. We can come up with a simple estimate of how much fines from this road will get into the creek over the coming year. This is a table showing the parameters for the site sedimentation classification. The total volume of fines are assigned ratings of very low, low, moderate, high to very high. The thresholds of each class may seem arbitrary, but do reflect professional evaluation. We took water purveyors, hydrologists, sedimentologists, road builders, and fishery professionals out on the same trip to sites that had been rated differently using the FREP water quality protocol. We asked these professionals what they thought of that site and what were the problems and how serious the problems would be to downstream water quality. The resulting classification thresholds were based on a consensus of where the group thought we had a problem and where we didn't. While not rigorous scientific method, it is useful because the diverse group came to an agreement when we are talking about very lows and lows. Most people don't get too excited, even if you are a water purveyor. When we get moderates, there are a range of flagged concerns. And when we reach the highs and very highs, everyone is more concerned, even the road engineer themselves saying, yeah, I can see we have a problem here. The volumes estimated to be generated are objectively acquired, but are most certainly rough estimates, but they are not subjective. Most water quality assessments in the past have been so subjective that two people going to the same site would get different answers. This assessment ensures that different people visiting the same site will get the same answers. By and large, we are finding that technicians, regardless of their background and the weather at the time of their visits, are rating sites in the same order of magnitude as other evaluators. The criteria is used to assess the site are known to all the evaluators, and the outcomes are reproducible. In order to demonstrate what different water qualities might look like in a stream, have a look at these beakers containing different turbidities of water. From left to right, we have 2 NTU up to 250 NTU. It shows the level of sediment you can expect at these turbidities. If you estimate both the turbidity and the discharge of the receiving stream, you can very quickly, in a matter of seconds, calculate the amount of fine material being carried by the stream. From this, you can infer that upstream from this site, there is a source of sediment, the proverbial smoking gun, generating at least this amount of fine sediment. What caused the sediment pulse? Sometimes it's coming from road sources, and sometimes it's coming from ditches or a landslide. Many times, it isn't coming from any recognizable human-induced sources. It's coming from riverbanks and from beneath the bedload of the stream. It is important when you see sediment load in the stream to determine where it is generated and whether it is being generated by human activities. All sites evaluated within the water quality protocol are chosen because we know in advance they are indeed caused by human disturbance. This table shows the effect on sensitive fish in varying sediment events. If we look at one specific site and we want to know what is happening immediately downstream from that site, we ask how a fish would fare upstream and downstream compared to the predicted impact on the stream. Note the severity of ill effects is a local, not cumulative watershed impact assessment. It doesn't have anything to do with overall impact on water within the watershed as a whole. You'd need to come up with an estimate of sediment loading of all disturbed sites upstream of the site, or at least a representative sample of them, to determine the impact on a main channel or intake. If we look at a small tributary with a discharge of 5 liters per second, bringing dirty water of about 100 NTU down to a large stream with 30 cubic meters per second, the impact on that little tributary stream would be very different, less than 100 NTU increase, than the impact of the site on the intake on the main stream channel, which would be only about 0.16 NTU increase. Overall watershed impacts are not necessarily the same as local impacts, but it's something people often don't recognize when they're doing these types of assessments. Here is an example of a little stream flowing approximately 100 liters per second. There's a ditch line coming in from the right side. Upstream, it's clean, and downstream, it's dirty. According to the analysis we have done, we know it's producing 5 cubic meters of fine sediment over 1 year. The discharge of the stream at bank full capacity is 100 liters per second. We calculate that the turbidity would be increased by 50 NTU over the 10-day period. According to the fisheries limits, that would be rated as a moderate impairment to the fish stream. This pie chart shows the percentage of incidents resulting from deficiencies within different activity classes. Here, I'd like you to recognize it doesn't matter what stage of the road's life it is in, there are always things that can cause problems for water quality, and road managers should be aware of these. With location, historically, the biggest problem was that pre-1980s, roads were often built right beside streams. There was no opportunity for sediment that was being generated by the road to be filtered before flowing into the stream. Design can strongly impact sediment generation. For example, if you have enough relief culverts along a road built adjacent to the stream, each small culvert can disperse a portion of the sediment load so that the fines and waters do not reach the stream. In construction, the main thing is to not leave bare surfaces open to erosion anytime you can help it. Where you know you will be generating fine sediments, have a transport route for that storm flow to direct the sediment to travel harmlessly to the forest floor. This map is an example to show you what kinds of things that can be done with the assessments. You can map out how much sediment is being generated at each site in your watershed and visualize where the low levels and high levels of sediment are getting into the water system. On this map, low levels of sediment generation are the green dots, yellow intermediate, and red dots are high levels of sediment generation. Next, look at the road system overlaid on your map and ask where your machines are right now. Can you go and fix something right away, and what should be prioritized? In this case, the red site is a bridge crossing where the sediment from both sides of the bridge, from about 250 meters on either side of it, was running all the way down onto the bridge deck and into the creek. This site could be greatly improved by just opening greater berms on both sides of the bridge approaches and would have given this watershed a considerably better rating. When you look at this list of sites, you will see there are different issues at different sites. Some you will be able to deal with immediately, and some are difficult or impossible to correct. For example, here at site 321, it's producing 1.1 cubic meters of sediment, but the issue is that it's too close to the stream. This problem is not easily remedied without huge expense. Ultimately, any natural resource extraction is a question of benefits and costs. When you go to a site, you are determining how much sediment would be generated in a year, and the methodology allows you to get the same results on a dry day versus visiting the site on a wet day. One thing to note is that when we were looking at experienced versus inexperienced evaluators, on a rainy day, inexperienced evaluators were found to rate the road surface quality as poor, whereas on a dry day, they would consider the same road surfacing quality to be good. Experienced evaluators and those with a knowledge of how the road stands up to heavy traffic when wet would be in a much better position to determine road quality correctly. For that reason, we have asked inexperienced evaluators or those unfamiliar with a road's condition when wet to rate all road surfaces as an average quality so as not to be unduly influenced by weather at the time of visit. You can see how much water is running down the surface on this rainy day on this road. Once the water dries up and a few pickup trucks drive by, it'd actually be hard to see that sediment had ever been moving on this road. So this concludes part 1 of this tutorial. Go have a break and then click on part 2 with your iPad handy to do an example assessment where I'll show you how you can enter the data onto the WQEE app. Thank you.